we start with 120 degrees. Coordination number of 4, we start with 109.5. And then you have to just subtract the 2 degrees for each. That's all I can say. I don't think there's a good way to memorize it. If there was, I'd tell you. Now we're going to get into some of our more complex molecules that have more than 4 bonds on the central atom. And we saw some of them yesterday when we were trying to do dot structures, like PCl5. We didn't do this one yesterday, we did one similar to it. I'm just going to do the dot structure of PCl5, save us time. There's PCl5. The phosphorus in the middle has 10 electrons on it. It's okay because phosphorus is big. James, do you have a question? No. Now, also to save us time, to me it looks very naked, but the chlorine should have the lone pairs on them. When you do your quiz and test, I want to see the lone pairs. Just want you to know that. What is the shape of this molecule? We have a phosphorus in the middle. It needs 5 bonds on it, and they all need to be as far as possible from each other to follow the Vesper theory.
Oh.
Now what we do with this one, oh my goodness, last hour I had some students that did not like this at all. They swore that there would be a better way to do this. Not all the angles are going to be the same in this shape. I'm going to warn you. So if you need all the same angle, you're in for disappointment.
Oh, no. Have fun, guys.
Thank you. The first 2 of the 5 are 180 degrees from each other. So we have like a head and a foot.
What is this one called?
And then the other 3 go along the waistline, like this. There's bond number 3.
No, it's like 1, 2, like this. 1, 2.
Here is bond number 4. And here's bond number 5. So along the waistline, we have 120 degrees of trigonal planar around that part. But they're going all in the same plane perpendicular to the first 2. All right? So what would you say about the bond angle on this one?
It's 120 and
some of them are 120, some of them are 90.
And some of them are 100.
Wait.
Chill.
One of them was 120, the other ones?
That's the bond angle for a coordination number of 5, 90 and 120. Now here is a computer model of this. There's PCl5, and you can see this angle right here is a right angle, but this one over here, that's our 120. See that? Now what is the name? We have to name this shape. This is new to everybody. I don't think any Chem 1 teacher talks about this.
Ours did.
All right, so we have to name this thing for the first time. There is a trigonal planar right in the middle. Do you agree that in the middle there's a trigonal planar? You got the 4 atoms, including the central atom, all on the same plane. Now, above that plane is a pyramid. Below that plane is an upside-down pyramid. And because of that, we call this shape a trigonal bipyramid. It means the pyramid up here, pyramid down there. Do you remember that, you guys?
Yeah.
JB taught you?
Yeah.
Oh, that guy.
Oh yeah. Wait. Why?
Trigonal bi. That means 2.
I did. I played
Can we take some time to think all those chemistries?
I rubbed off on
If you
that.
insist. Prox, I don't want you to take credit for that.
You know, I look at it.
I would take some time to think them. I'm not going to do something like square guessing.
No, they stay. They stay. These atoms are there to stay. They don't jump around. No runs.
It's like centimeter squared, but like pyramid squared.
Pyramid square.
Yeah. Yeah. These 2 are fixed.
Like they'll name it like TP and then squared.
I've
It's
never
like
heard that.
it's like the area.
They just name the whole thing in one. Yeah.
Then turn out to be like an SP2 hybridized orbital.
Funny
Wait,
things happen in the 4th hour.
Did you say I like that? Yeah, we're fun.
All right. Any other questions about PCl5 and that trigonal bipyramid?
what would the SP hybridization be?
We haven't even talked about hybridization yet, but you have to wait on that one.
Oh,
We'll
okay.
talk about it. Probably tomorrow. Okay, now, let's see, how are we doing for time? We have 2 other coordination, no, 3, oh boy. I was going to ask you to do the dot structure of because we have lots to do. So the TeCl4, very quickly, we're going to do this together. If I had more time, I'd say, hey, try the dot structure of TeCl4 because it's a little weird. But we're just going to do it together. Te is a big atom in the oxygen family. It's underneath selenium. So it's got 6 valence electrons. And then you have 4 chlorines, which you have 7. So you got 28 plus 6, 34 electrons. If we know that Te goes in the middle, and that's a pretty safe bet, we have the 4 chlorines. Now remember, the chlorines are going to have all the lone pairs. I'm not going to do that. How many, if you imagine 3 lone pairs around chlorines, how many electrons are in this structure? That's right, there's 32, right? There's 8, and then they're all identical, so it's times 4 is 32. But I need 34 electrons. How do I put 2 more electrons in?
Add another one.
Put them on the central atom. And now where, I don't even have any place to put them. Well, just put them someplace. I know, it's so weird. So, what's the coordination number on the Te? 5. You have 4 bonded atoms and 1 lone pair for a coordination number of 5. So the general shape is like this, where you have the trigonal bipyramid. But one of these needs to be a lone pair, so I need to take it out. Which one do I take out? Do I take out one of the head or feet, or I take out one along the waist?
One along the waist.
The one on the...
Now, if I take out one of the head or feet like that, now I only have 3 90-degree angles. I got this big open space. What we find is that the sum of the angles is minimized, or maximized. We need to maximize. That's Vesper theory. They want to be as far apart as possible. This is more far apart than taking one at the top and bottom. And what would this shape be? Here's a computer model of it. I can't find. Oh, there it is. So that's it's showing it like this. I had. Oops.
Oh. Nice job, buddy. Shoot. Nice.
How would you know what? Sorry, it's crooked.
You're right.
Ask me again, Sophie.
Based on the Lewis structure that you made, like for example, we did the H2O, we could have done the HOH. So how would we know if it was bent?
You have to know what the shape is. You have to know the O has 2 lone pairs, so you say, okay, O has 2 lone pairs and 2 bonds. Its coordination number is 4. 2 lone pairs means it's bent.
Okay.
That's how you know. Even if the dot structure is written differently from what the shape is, you have to be able to determine what the shape is. Okay. How do we name this shape?
I truth, please say it.
All right, you do. Here's what they've done, and that's why I had this thing on its side, is because if I put it over on its side, then you can visualize the shape a little bit better. It is, I just crack up at scientists sometimes. Imagine this.
Oh, seesaw.
It's a seesaw shape. That's what the official name of the shape is. Seesaw.
Good job.
Teeter-totter. They'll accept it. They will.
Square up in a little when you have 2 lone pairs.
So, the Zoom dolls would call it seesaw. Others that don't use the term seesaw, not teeter-totter. Too many kids.
Are they serious? This is official.
That is the name. It's a seesaw shape. Yep. Okay, now what are the bond angles? We have a lone pair. It spreads out. It causes squeezing.
120 and 90.
Okay, now I'm going to tell you this. You know how we have the squeezing going on? Does it squeeze a full 2 degrees? No, not quite. Because we have so many remaining bonds on here, this one is not going to give us the full 2 degree squeeze. When there weren't so many bonds, then yeah, we get it. So here's the way we do it. We say less than 90 degrees and less than, but not great, sorry, yeah, less than 120. So we're not going to actually give it an angle. But we just recognize that because of that squeeze, we're going to have just under 90, just under 120 for our angles. So we get this kind of thing. Ooh, it gets pushed over. I'm exaggerating so you can see it. Questions on that? Teeter-totter, how fun.
Why is it like teeter-totter? And why is it a seesaw? Because there's no...
Looks like a seesaw.
No. Like why?
Now, we don't have time for this.
Because
ICL3, same kind of thing is going on. I's got 7 electrons and CL's have 7 electrons, so we need 28 on this thing. So we have an I and 3 CL's. And lone pairs around the CL's and then a lone pair there. So let's see. Count the number of lone pairs. Oh, the total number of electrons.
it is an H class.
Oh, wow.
There's 26 electrons in this, but we need 28. So we need to add another 2 electrons. To what?
Iodine.
I'll get to the iodine. So, well, where do I put it? Put it anywhere. Just put it on there.
Seems like a trigonal
Put it
Bipyramid.
off.
What's the coordination number of the I? It's another 5 because it's got 3 bonds and 2 lone pairs. So it's got 5. So it started as that trigonal bipyramid. 1 has already been taken out of this. So there's our starting point like that. Now I need to take 2 out. The way that we assume that it happens is like this. It's a T shape. Take 2 off of the waistline. So now you're just left with 1 of the waistline, 1 in the head of the foot. And so it's a T shape.
Would there ever be a?
Yeah. There it is. It's on its side, but it is officially a T shape. The angle here is 90 degrees because the squeezing is happening symmetrically. And so, yeah, it kind of cancels out. Sir?
If we have NH3, we have 107.5, but when we add a lone pair, how does it become 90? We added a lone pair to the central atom.
2 lone pairs on this.
No, but we added 1 lone, because NH3 has 1 lone pair, I2 has 2 lone pairs. So if you add an extra lone pair, how does it become 90 instead of 107.5?
For which one?
For this one. Because NH3 has 1 lone pair.
NH3 is a coordination number of 4. It's a different game now. We have 5 orbitals that are spreading out now.
So you have more electrons on the top, so you would assume that the other ones go even
Yeah,
down.
but then the other
even
ones
more.
are pushing on that.
Yeah, so you got electrons here pushing and
Right.
here pushing.
Equals out.
Here's a pair of electrons. Here's a pair of electrons, right? And so they're, I don't know, you can't really see it, but yeah, they're kind of, you got a pair out here and a pair out here, and so it winds up at 90 degrees.
Let's just go on.
All right.
I swear I didn't do anything.
Now, I'm going to skip the I3 negative. I think we've done enough with the coordination number of 5. Let's just jump to the coordination number of 6 and the sum. 3. 3 shapes in this one.
No.
Oh, this is it. This is the last one.
Oh wow. See if happy.
Tomorrow, can I leave my stuff here when I go for the M?
Yeah, all of you juniors, if you're going to the M step from here, you can just leave your things under the big table over there. Now, I will tell you, 6th hour is a Bio B class in here, and I'm going to be very, very straight with you. Bio B kids are... turn me off for a second.
Oh,
No, turn it off.
I'll turn it off.